So as you said, I will be speaking about constraint controllability, hopefully in a way that introduces the subject. So those of you who are not control theorists can follow along my talk. So this is joint work with two people, Emmanuel Trella, who's a professor at Laboratoire Jacques Lyons in Paris, and Christophe Zang, who is a postdoc at INRIA Nancy. And let me just give you the, okay, there you go. So the flavor of what control is about. So control theory is about starting from some model, can be an ODE or a PDE. So derivative of y with respect to time equals f of yu, here put in a very abstract form, starting from some initial condition. So y is the so-called state, and u is the control. This is what you choose in these problems. So x and e will be Banach spaces, abstract linear spaces. And if you want to think of a specific kind of control model, you can think of a linear control problem. Derivative of y equals ay plus bu. And if you have an ODE, then a and b are just matrices. And actually, most of my talk will be about linear problems, so of this form. And what is the aim of control theory? Motivated by applications, you pick the control. For each control, you have a trajectory of the equation. Given some fixed time t, final time t, some horizon, initial condition, and what is called the target, yf, what you want is to find a control that steers the equation towards the target. So this is called the problem of exact controllability. You want to end up exactly on the target that you've been prescribed. And there is a weaker notion of controllability that will be also important in my talk, is approximate controllability. So you're a bit less ambitious. You're just asking to be able to find a control that brings you to at a distance epsilon from the target that you're given. These two notions might seem very close, but in the infinite dimensional case, making the distinction is important, as you'll see. And usually what control theorists do, once they know that controllability holds, so if there is at least one U that exists and that does the job, you want to find an optimal control. So you want to steer a given system to a given target, and you want to minimize, I don't know, the fuel, or you could even minimize the time to reach the target. So among all controls achieving the target, you want to find the best one, given a certain cost that is given to you for whichever application you have in mind. And the questions that we try to tackle in optimal control and control in general is the existence of a control. That's the controllability question. And once such a control exists, you want to compute, at least theoretically or numerically, a control or the control, if there is a single control that minimizes the cost. So this is the goal of control theory.
Sorry.
Yes?
And are you not interested in uniqueness of the control?
Of course. So once the optimal control is posed, uniqueness here is, so the control, typically we would want to wonder if this here we have a minimum and there is a single control that minimizes that. So this is a typical question that we have in mind as well. Okay, so just because as you saw in the title, what I'm interested in this talk is constraint controllability. So the control here does not lie in the Banach space E, but it lies in the smaller set. There are constraints on the controls, and obviously in applications this is what happens. You're given some constraints on whatever fuel you can use. Of course, this is quite natural. So just as a warm-up to understand what constraints can bring to the problem of controllability, consider the simple 1D ODE. So derivative of y with respect to time is y plus u, starting from some scalar initial condition. And the constraint that I'm looking at here is the unilateral constraint. The control has to be above -1. So that implies that whatever you do, whatever the control, the solution of the ODE will be above this function of time. There's no way around it, okay? So let us assume that we want to reach the target yf equals 0. We want to reach the scalar 0. Then there are obstructions to controllability. First, there's an obstruction in arbitrary time, meaning that if the initial condition is above 1, because of this inequality here, there is no way you will reach 0 because the solution of the ODE is above 1 at all times. Okay, so whatever the time that you're given, the capital T, there's no way you can reach the target 0. And you have some weaker obstructions to controllability in small time, for instance. Now, if the initial condition is between 0 and 1, then if you were to find a control that achieves the target 0, this inequality tells you that the time capital T has to be at least this quantity. So it has to be large enough. Okay. So that's also quite natural. If your initial condition and your targets are far from another, you might need enough time to reach the target. Okay. And most of my talk will be on the heat equation. For those who do not do PDs, let me just quickly recap what the heat equation is all about. So the heat equation describes the temperature in, say, a room, say this room, so in some set omega. So y of Tx is the temperature at time t in position x. And the PD satisfied by the temperature is the following. So you have the first equation that tells you a link between the space and the time derivative of the functions. You have an initial condition. You have to prescribe what is the initial temperature in the room. And you have boundary conditions. For these equations to be well posed, you have to specify what the temperature is at the boundary of the room at all times. So here you see this is the boundary of omega. At this stage, there is no control in this equation, but you can, of course, and this is typically what is considered in applications, you would have a source of temperature, so say a heater in the room. And so here you have a U of Tx on the right-hand side of the equation, which is your control. This is what you choose. The temperature at all points T and position, at all times T and positions X. And one typical thing that you would do is you would say, well, the control will not act on the full domain omega, but on a smaller domain. So here, key of omega, key of lowercase omega, is to say that the control is 0 outside of a small domain. That would be where, say, your heat source is a position. So the situation is like this. You have omega here, and lowercase omega is, say, here. And this is where your control is active. And same question, you may wonder if you're able to reach a certain temperature distribution in the room that you've been prescribed, been given. You can also imagine that you do not control what happens inside the room, but only what happens at the boundary. So you heat, say, the room from the boundary. So it is not another possibility to consider control, so-called boundary controls. Okay. So again, my talk will be devoted to the constraint controllability question for the heat equation, but I just want to spend some time on mentioning some results on a related model, because at least for these results, I have simulations, so I think it will give you a grasp of what can happen in terms of controllability. So here, this is a bit of a detour through population dynamics. So let me start by explaining the modeling. So you have you want to describe the density of individuals. So these individuals are densities between 0 and 1. There's just no 1. And 1 is the maximum density of individuals that the system can have. And usually the model that you've all seen, I think, is the logistic model. So there is exponential explosion of the number of individuals near y equals 0. And here there is a saturation effect. So this is the logistic growth. So this is the most common model you can think of for population dynamics. So that means that the density of individuals is indeed between 0 and 1. And here I will mention a common generalization of this model. It's called the bistable equation. So there is a third term that appeared here, y minus theta. And what is the rationale behind adding this term? It's called the Ali effect. So here is the typical function f that you obtain with such a form. So the idea is to say that if the density of individuals is below theta, well, individuals are not, you don't have enough individuals so that reproduction can take place, for instance, so the population will die out. Whereas if there are enough individuals, so above theta, then the population can actually grow. So this is a bistable, so-called bistable function. So here for this ODE, let me just mention that 0 is a stable state, 1 is stable as well, and theta is unstable. And the link with what I mentioned earlier with the heat equation is a more general model for population dynamics is to mix this ODE with movement of individuals in space. So what you have is, starting from the ODE, you have now a PDE where the individuals move in space. So the term here is to account for diffusion of individuals who move randomly in space. And you have this f of y, the function that I mentioned earlier. And for simplicity here, most of our results are in this simplified setting. I will assume that omega is just an interval. Okay. And so far there is no control. And the control that we consider is control acting at the boundary. So at 0 and at capital L, namely the two ends of the interval on which the equation takes place. And again, imagine if we were in higher dimensions, say in 2D or in 3D, you have, say, a forest where there are some whichever species you're interested in, and you want to control the density of individuals inside the forest by acting at the boundary. This can be by killing the individuals if you want to limit the spread of the population, or instead bringing new individuals from the boundary. So this is the motivation for such types of control problems. So of course, the controls have to satisfy a constraint. They cannot be less than 0 and above 1. This is the density constraint. So here there are natural constraints on the control just by the motivation. And again, the control question that I want to address, so I won't mention any theoretical results on this subject, but mostly simulations to give you some intuition. So we would typically want to control the equation towards the 0 state. So there are no individuals, or a compromised unstable state theta, or possibly the invasion of the whole population, depending on the application you have in mind. And what I like about these simulations is that they show you what types of obstructions to controllability you can have in these settings. So here, this is our interval 0, 7. The initial density of individuals is constant, equals to 0.9. And you want to bring the population to 0. You want to kill everyone. It's not very nice, but that's what you want to do. So certainly the natural strategy is to kill people at the boundary. You will not bring new people from the boundary. This mathematically can be proved that this is the best strategy. And this is what happens when you do that. So here you see at the boundary 0 and 7, you have 0. And certainly the strategy is successful. You bring the population to 0. And now a new simulation. You might seem that this is the same simulation. This is you have to spot the difference. Difference is the size of the domain here. So here beforehand, the size of the domain was L equals 7. And here the size of the domain is L equals 11. So the domain is a bit larger. And this has a strong effect on the success of the strategy. Namely, now if I put 0 on the boundary, the strategy fails. And the equation seems to converge. Actually, it's a stationary state of the equation. So here there is a so-called obstacle to controllability. And this is because the domain is too large. You may act from the boundary, but it's not enough to actually have an impact on the full domain. So this is a typical obstruction to controllability, and this can be proved rigorously. And what we proved, so this work is with Emmanuel Freda and with Enrique Suasua, who's at Erlangen in Germany. What we proved is that this phenomenon holds not only for reaching 0, but also for reaching the compromised state. We call that, there's also an unstable state theta. And to reach this compromised state, it's clearly not as easy as 0, because you might want your control to oscillate between values that are below or above theta. And indeed, this is a simulation where if the domain is small enough, so this is this computable threshold, you can, by control strategy, manage to get the population to the constant steady state theta, so as you'll see. And the strategy goes as follows: you let the population go close to 0, then you start putting a lot of new individuals at the boundary, you'll see here, and then 0 again, and then you have to oscillate very quickly between 0 and 1. So it's not an implementable strategy. This one is difficult to implement because this is a strategy that's built to reach a target as fast as possible. So you can have strategies that are a bit less ambitious and that are a bit less oscillatory, so more realistic. Okay, so it was just to give you a feeling of these kind of questions that we can try to tackle. And now I'll move to something a bit more theoretical on the heat equation. namely, I won't have simulations to show. I hope next time, maybe. So recall, this is the heat equation. This is the temperature in the room. Here, the boundary conditions are 0. You can imagine that this is 20 degrees at the boundary of the room, and then you can always, without lots of generality, you can always go back to 0 if you want. And you have a control that's acting not in the full room, but only in a prescribed subdomain of the room. So you have to believe me that this is actually, it seems linear, and it is linear, so it can be cast in the general form that I mentioned at the beginning. So derivative of y equals ay plus bu. And here, there are some functional spaces in which the equation is well posed. So the space of squared integrable functions and the control space is the following. It's not very important. Just to say that we have these Banach spaces to work with. And here are the known results that date back to roughly 40 years ago already, which are kind of puzzling when you see them for the first time. So these results, they say the following. Whatever the lowercase omega you take, so you can take a very tiny heat source in the domain, then whatever the target, yf, whatever the initial condition, whatever the time, whatever the epsilon, you can find a control that brings you very close to the target. Okay? So this might seem surprising, but again, recall that here there are no constraints. So even if the initial condition and the target are very far from another, and you have, I don't know, a few seconds to reach the target, well, this result says you can do it, and obviously what you expect is that the control will take arbitrarily large values, positive, negative values, which obviously is not very realistic. I mean, it's not very realistic, it's not realistic at all, but this is why this result holds true. The second result that's maybe slightly more, that's also surprising if you're not into PDEs, is that the heat equation is not exactly controllable. So although you're able to reach a target to arbitrary precision, you cannot reach it exactly. And the reason for this is pretty simple. So let me explain the two ideas behind these two results. So the first result, that's the tough one for sure. It's a constructive approach that I'll mention later on, because essentially our approach to constraint controllability builds upon this constructive approach. There are lots of approaches to prove the first result, and one of them is based on dual arguments that I'll come back to later on. The second result is easy to see if you are aware of the so-called regularizing effect for the heat equation. So what does this say? Say whatever the control that you use, the heat equation is regularizing, meaning that everywhere outside of the action of the control, the solution is extremely smooth, it's C infinity. So of course, if you want to reach a target that's not smooth, well, you cannot do it because of this. So the non-exact controllability is due to the regularizing effect of the heat equation. Okay, what types of questions do we try to tackle? If we try to tackle with, this is ongoing work, but these results are now stable, with Emmanuel and Christophe. So we want to control the heat equation, but we want to consider constraints. So the types of constraints we look at, we say at all times, the control must be in some constraint set. And the first requirement is we want to actually hit the equation, namely, we want the control to be non-negative. Okay, so every time you see a capital U here, then this set has to be included in the set of non-negative functions. So I just have to introduce one notation that's standard for in PDEs. The semigroup, again, the notation itself is not very important. What it says is that you can give a name to the solution of this equation without the control. Okay, so the free solution consists in putting u equals 0 here, and you can compute what the temperature is at time t. And this is what I call STY0. And quite intuitively, there is a monotonicity property of the heat equation. You cannot do better than this, namely, if you do not hit the equation, if you use no control, u equals 0, well, this solution is always a lower bound to the solution of the equation with a control. It's quite natural. So the solution of the controlled equation is always above the solution without using the control. Okay, also, again, very natural. So there is a first obstruction to controllability. It's in the spirit of the one that I mentioned in the ODE case. Recall that I had this U must be larger than -1. Here I have U larger than 0, and the same type of idea applies. So clearly, if you want to have a notion of approximate controllability in the setting where controls have to be non-negative, your definition has to take that into account, take these obstructions into account. So we will say that the system is non-negatively approximately controllable under the constraints that were given if for all epsilon, for all targets and initial conditions that are ordered according to this obstruction, then we can find a control that leads the system to YF up to an error epsilon. Okay, this is a natural notion of controllability given this obstruction. L2. L2. So all possible reasonable function you can think of. So certainly, given what I've introduced earlier, the first idea is to first try to understand what happens if you do not constrain too much. You first start with the controls have to be non-negative. This is your constraint set. Okay. And you want to be at least a bit ambitious, as we were with the unconstrained case. We want to force the control to act only on a certain subpart of the domain. Okay. And you would hope that you get the same result, namely, you have approximate controllability in this case. And the first result that we proved is that this is not true anymore. So there is an obstruction in small time. And this obstruction tells you that if the time t is too small, then the system is not approximately controllable. So it might be surprising because you could think, well, once you've taken into account the first obstruction, then you should be able to do the same, but it doesn't work. So let me just mention that this result is not completely new in the sense that in recent literature, there has some similar results have been obtained for the same type of question for similar equations. So this is known that these types of obstructions can occur. So I will skip the proof. I'll just mention that the proof is inspired by another a work that's close to this equation by Dario Pigin and Enrique Suasua. And I will just want to mention that this approach is based on this equation, dual equation. This equation will be critical going forward in the presentation. That's why I want to introduce it now. So you have your heat equation with a control, and you can consider another equation, which is called the backward heat equation. Why is it backward? Because here you see you have a plus, whereas for the heat equation, I had a minus. So this is the backward heat equation ending at some PF, which is given some PF in X, some function PF. Okay, and you can look at it in the opposite sense. So if you change time, it's the same as starting from PF and letting the heat equation evolve. So this is maybe a bit abstract at this stage, but this equation will come back later on. So I'll just give the proof of this result. The result is not maybe it's 1 page long, 1.5 pages. It's not crazy. Okay, so once this has been taken into account, there is no hope to get a controllability result when the control cannot act everywhere. But of course, you don't want your control it's not realistic to have a control acting everywhere. So we are still a bit ambitious about this. So we want the control to, at all times, to act only on a subpart of the domain. So this subpart may move with time. So it's like you're moving your heat transfer in the room. But you'll see that we'll have to deform the heat transfer. So forget about applicability at this stage. This is rather theoretical work. But then you can do simulations with more realistic constraints, as I'll maybe mention at the end. So now the control is acting only on omega of t. And omega of t, we're still ambitious, as I said. So this omega of t has to be a measure that's fixed a priori. And it cannot be bigger than some value that we have chosen. So here, ML is some fraction of the measure of the whole domain, okay? So in other words, as time evolved, this is maybe omega at time 1, and then you move your domain, this is omega at time 2, etc., etc. And you're forced to have a measure that's less than this ml. And actually, we're a bit more ambitious than that, because typically what you would want, so I will go back to applicability, but this is debatable for sure, but you certainly don't want to have your heater have different temperatures. Usually the heater you use at home, you cannot say, well, on this point of the heater, I want 19.5 degrees, and here I want 0.2. So you want a uniform, a fixed, constant temperature all over the heater. So this is what we do. We further constrain the problem. We want the control to be of the form an amplitude, m of t, times the indicator of the set. Okay? And this amplitude can change over time. So certainly one way to phrase this, forget about the theorem for now, is to say that the constraint set that we're looking at is the set of controls that are in this set. That can be written as an amplitude, capital M, and an indicator function, lowercase omega. Okay, so at all times, U of t must be in this set. So there must exist an M of t and omega of t such that the control writes like this. And what we proved, and this was the main result, is that in this setting, the heat equation is indeed approximately controllable. And we again have this result that the domain of action of the control can be as small as we want. So for all L in 0, 1, for all times, we can steer any initial condition to any target as long as they are ordered according to the constraint that we have because of the non-negativity constraint. Okay, so the rest of my talk will be devoted to, check the time, to trying to... Here?
Capital M is for every capital M can exist one.
Yeah, that means that then here it means that for all epsilon, for all yf or y0, exactly.
No, capital M in the definition of the concept.
This one, it's an amplitude. It's a scalar.
Any yes, but any arbitrary small.
Yes. Then we'll see if probably I won't have time to mention it, but then you can look at what happens if you bound from above this. You say, I don't know, I cannot use more than 20 degrees, say. So then you can have an upper bound for this amplitude. At this stage, I do not put any constraint. So, yeah, thank you. So again, yeah, the rest of my talk is trying to convey some of the ideas that are behind the proof of this result. Because I think there are some kind of nice ideas coming from optimization and convex analysis that allow us to prove this result. So first, I'll try to explain how people try and tackle the problem of controllability without constraints. And this sentence might seem very weird at first glance if this is the first time that you see this. So typically, this is for people doing optimization. This is probably not a surprise, but let's say you have a set A and you are wondering whether this set is non-empty. Okay. Maybe this is a set defined by lots of linear inequalities, and you don't know if there is at least a point in this set. This is the question you try to tackle. And optimization, people doing optimization will say one way to do so, one way to try to answer this question is to look is to choose a function f. So f at this stage is something that you have to choose because you have some some knowledge, some know-how about optimization. And you minimize over A. So this is very weird because you don't know if A is empty or not. But you're back to now the question, is A empty, is related to the question, do we have this? So if A is empty, this is plus infinity, and conversely. Okay? And once you have phrased this as this question, you can use tools from optimization. You can look at the dual problem of this, the Lagrange problem, like Lagrange dual, and so on. So here, the idea is kind of the same. It's actually exactly the same. So we want to find U that brings the solution to YF up to epsilon. And in fact, this is equivalent, this is exactly what I wrote here, to that there, for a given f function from e to r, and can be plus infinity also, to prove that the infimum of f of u is finite. Okay, so here you see it's a constraint problem. This is not a constraint, this is the Banach space, but this is the constraint. U has to bring you near the target. Okay, so the question is this infimum finite or not? Then there's a second trick. It's a common trick also in optimization. If you don't like constraint problem, you can consider the equivalent problem that's unconstrained. So how do you do so? You want to minimize f of u. Okay, f is abstract here at this stage. We don't know what f is, but whatever. And you remove the constraints by putting them in the objective function. So it's a very standard trick in optimization. So you want to minimize over, there's no constraint, f of u plus a function that will be plus infinity if you do not satisfy the constraint, and 0 otherwise. Okay, so obviously these two, this is just really one trick to rewrite the same thing, but at least you have a non-unconstrained problem. So here is the function, it's just what I said. Okay, so now there's a bit of notation that I won't be mentioning, I won't be using too much, but let me just mention that here, recall we have our control problem, and when the problem is linear, you can use Duhamel's formula. You can compute the solution of the equation at time t as the contribution of two terms. One, that's the free equation with u equals 0 plus a linear operator, which takes the control as an input. So that this function g of LTU can be written in a more compact form. It's just a notational kind of way of writing thing that will be useful later. So in other words, here, what it says is that reaching the target is equivalent that the linear operator LT applied to your control U has brought you to this ball. And this ball is, you just translate the target by whatever is needed. Okay, I'll come back to it. Okay, but now remember that we are interested not in unconstrained controllability, but in constrained controllability. So we want to find an f for which first, we want to be able to say that this is finite, which will mean that there is unconstrained controllability, but also we want to choose f wisely enough so that the constraints are imposed. There are two ways to do so. One way is like brutal, is to say, well, I'll pick f of u to be plus infinity if u is not in the constraint set. Then certainly, whenever f of u is finite, then u satisfies the constraints. But that might be too brutal. A more subtle approach is to find an f such that whenever u is optimal for the problem that is here, then necessarily u has to be in the constraint set. Okay. Why can this be used? Because usually when u is optimal, you can write some optimality condition. So you have some information on u. And you can hope that these optimality conditions will tell you that actually, if f has been chosen appropriately, then u satisfies the constraints. So you see, this is interesting because the way I introduced control, I said, first you look at controllability, and then if controllability holds, you look at optimal control. And here you see that somehow you can use optimal control to investigate the question of controllability. Okay, and this is really based on this idea from optimization. Okay, so this is for those who are, as was my case maybe 1 year back, that's convex analysis in a nutshell. So I'll try to not kill you with notations, but for those who are not used to tensile conjugates and their friends, like subdifferentials, we just quickly mention the ideas. So you have a Hilbert space and a function from the Hilbert space onto R. And the tensile conjugate is really the Fourier transform of convex analysis. Okay. So maybe the formula itself is not important. You have a function f, you can compute its conjugate. Okay. And let me just introduce the ideas rather than directly on the formula, but rather on examples. So if you have 1/2 of x squared and you conjugate it, you end up with the same function. Okay. And then you can look at the LP norms. So if you have 1 over p x to the power p, then you get this function, the dual function, with the dual exponent q to p. And that conveys the first intuition behind Fenchel conjugation. You see that if P is large, so you have a function, say x to the 4, that goes very quickly to infinity, then this function, on the contrary, will go to infinity, but very slowly, okay? And really, Fenchel conjugate, you have to think about this. The faster the function goes to infinity, the slower the conjugate will go to infinity. And the extreme case of this is for p equal 1, obviously. So if I take p equal 1, so a function that goes linearly to infinity, absolute value, then its conjugate is a function that goes dramatically quickly to plus infinity. So here, this is a notation from convex analysis. This function is 0 on -1, the interval, and is plus infinity elsewhere. So certainly that's a function that goes quickly to plus infinity. When you're outside of -1, 1, the function is equal to plus infinity, okay? And you have this result holds more generally when you take the norm and you conjugate it, you end up with the indicator of, in the sense of convex analysis, of the unit ball of the Hilbert space. And this is the notation that I was just mentioning for some set C. Its indicator in the sense of the convex analytic, in that convex analysis world, is this function. And what will be important is the so-called support function. It's just a notation, sorry for another notation. It's the conjugate function of the indicator, okay? And as you probably have guessed from the examples that I gave, you would expect, like Fourier transform, that if you conjugate twice, you end up on the same function. This is true in a good set of functions, and this is the so-called gamma is usually called gamma 0 of h. Again, it's not important if you're not familiar with this, but just know that there is a good space of functions. You need convexity is the most important thing, and some regularity, for which conjugation is an involution, if I have to be pedantic about it. Okay, so now I won't speak about some differentials, but I hope I'll mention it along the way. So I see that my time is passing. Okay, so let's go back to the problem that we had. We had this problem. Recall that we were looking at this optimization problem, and we saw that in choosing a good function f, we hope that this will allow us to investigate the question of unconstrained or possibly constrained approximate controllability. And any person doing, I don't know, math applied to imaging or doing optimization, when he sees this, he wants to take the dual. It's Pavlovian. And that's why I call this problem the primal problem, okay? Because then you can take the dual in the sense of Fenchel. So again, if you're not familiar with notation, it's not important. Think about Lagrange duality, for instance. You have a primal problem, you can look at another optimization problem, and these two problems are related in the sense that the infimum of this problem is always larger than the supremum of this problem, or minus the infimum of this problem. And of course, just as in Lagrange duality, maybe I should say Lagrange duality, the best case scenario is when you have strong duality, when pi equals t. And this is a very famous theorem in convex analysis called the Fenchel or Rockefeller theorem. Under weak hypotheses, so in general this is true, strong duality holds. So here pi is the same as this d here. And there is another consequence that's also nice. We'll be interested in saying that there exists optimal controls. So we want a minimum here, not merely an infimum. And under the assumptions of the Fenchel-Rockefeller theorem, if you can prove that this is finite, so pi is finite, then it is attained actually. Okay. So why is this theorem so important for us? Because recall that we want to look at pi. We wonder if pi is finite, and this is essentially the controllability problem. And if looking at d instead of pi is easier in some sense, then we will certainly try to look at d to prove that d is finite. And this is indeed the idea of the approach. Okay, there is another thing that I want to mention. So again, maybe let me just go a bit quick here. So as in Lagrange duality, there's a saddle point problem associated to this duality. And what is important is this condition. You want to be able to write optimality conditions for an optimal control. Okay, if U is a control that is a minimizer for this problem, you want to write gradient of U gradient of a function at U equals 0. So in the setting of convex analysis, it's a subdifferential, it's an inclusion. So you get this inclusion. So in other words, this is the type of optimality conditions you can use in the framework of convex analysis and these type of optimization problems. Okay, so let's take a break, just 1 second break. We want to look at the controlled heat equation. And as you may remember, this can be put in this abstract linear control problem formulation, where the function f, there's still, haven't told you which f we choose, so this will be the whole question, okay? And g is fixed. G tells you we want to reach the target, okay? So this g is 0 if you reach the target and plus infinity if you do not. So here you can compute the dual problem in the sense of Fenchel. And here you have an abstract f star, the Fenchel conjugate of f. And here it's just computing the Fenchel conjugate of this function. So you have to believe me to get this function. This is the function I call j of pf. So for us, this is a critical function because we want to investigate whether d is finite or not. Okay. So let me now say a few words about this function, because you see here what happened, what appears in this equation is the adjoint operator of LT. And this adjoint can be computed. It's a bit complicated, but let me just, again, what's important here is that this adjoint equation, this adjoint operator that we have to deal with, because it appears here, so there's no way around it. Well, you see that there is this dual equation that I mentioned earlier. So for some reasons given by this framework, we have to deal with this adjoint equation, because this is how the adjoint operator writes naturally. And actually, I won't explain exactly the details, but the unconstrained problem results that I've mentioned that date back to 40 years ago, one way to prove them is to use this approach with a good choice of f. Okay, just so you know it's possible. Okay, so what is the methodology? And then I'll probably go briefly over the rest, but just I think if there is a take-home message, what I find interesting about the methodology is this. So we'll pick a cost f. I haven't told you yet which one we chose. In general, if you don't pick a very weird f, there will be strong duality. Okay, pi equals z. But you don't know yet if this could be, it could happen to be pi equals z equals plus infinity. Okay, this is the case where the problem is uncontrollable. There's no controllability. Okay, so the question now that you know that pi equals d, is to investigate whether d is finite rather than whether pi is finite. And this can be tackled. It's the usual approach in optimization. If you want to prove that the function has a minimum, you will try to prove that it's coercive, that it goes to infinity at infinity, and then you're back at looking at compact sets. So here we are in finite dimension, so this is you have some weak topology involved, but that's the same idea. And then our hope is that we've chosen f in such a way that whenever f of u is finite, then u is in the constraint set. Then we're done. Okay, victory. And if this is not enough, and this is not enough in our case, then we look at optimal controls. We know they exist, we can look at them and hope that the optimality conditions, remember that these were these abstract conditions, the optimality conditions, are such that whichever the optimal control you get, this control has to be in the constraint set. Okay. So this is the methodology. There are two things to do. Actually there are three things. One, pick a very smart f, which is not obvious at all. Then prove that the problem is the dual functional is coercive, and then look at the optimality conditions. Okay. Let me see. Let me know when I think I started a bit late, but maybe we're at 45 minutes, maybe roughly at this stage. Okay, sorry. Maybe if I'm okay, maybe if okay. So of course, at some point we have to go back to which constraints we actually have to tackle. Because that the constraints that we had are these what we call shape controls, controls that are an amplitude times an indicator function, and that they can evolve over time. So this is the constraint set. And of course, any control in this set can be written as an amplitude times an indicator function. So this is just one maybe complicated way to say that the constraint set that we look at is the homothenity or all possible homotheties of this function, of this set. And let me just mention that you see that this set is actually a cone. Okay, so it's not any set. From the convex point of view, well, it's a cone. This is not too bad. But I shouldn't have said from the convex point of view, it's non-convex. If you had two such functions, you do not necessarily end up with an amplitude times times an indicator function. So it's non-convex. So that's bad because we are in the framework of convex analysis. We need convex sets. And this is, I think, another interesting idea from convex analysis. So an optimization. Let's imagine you have a set like this, and it's not convex. So typically, let's say the set is this one, just the parts of the boundary of the sets. So this set is non-convex. I should use another color, but again, this is the set I'm considering, the union of these two. This is not a good example, actually. Maybe I should do that. So this is your set. It's not convex. So if you want to pick a convex set, certainly you will consider the convex file of this set. So we consider this set. Okay. And typically what you do in optimization and in optimal control, if you have non-convex constraints, you will consider the whole of this set and then hope that actually the optimal controls are at the boundary of the set. So you solve the problem here on the whole set, and then you hope that actually you end up at the boundary or at the original constraint set that you were given. So it's called the relaxation of constraints. So here, if you look at the convex hull of this set, these are all functions that are between 0 and 1 and have a total mass of at most ml. Okay, you have to believe me that this is the relaxation of this constraint set. And there is an important property, is that the original set, the one we're interested in, is exactly the set of extremal points of this set. So the extremal points, so if this is the, let's say we look at this set, the extremal points are the vertices. Okay. So then as time is ticking, so using these ideas, we are relaxing the problem, looking at convex constraints, and then trying to see if instead, actually the optimal controls are at the boundary or at the vertices of the convex set. That allows us to pick an actual cost. So this is a bit technical, so I won't enter into the details. Let me just mention the ideas. So recall, we want to look at this function, and our aim, we need a function that's coercive. So this function has these parts of the functions are homogeneous of degree 1. Okay, they don't go to infinity very quickly if ever they were to go to infinity. So the natural idea is to put something quadratic here. Okay, so that it has enough, it goes to infinity sufficiently quickly to win over the other terms. So this is what we do. We use quadratic terms, and I'll just unfortunately, we were going to take baths, but I won't have time to refresh you with this. But what I want to mention is, in the end, so here it is. So I know you've been waiting for it for the whole presentation. What on earth is the F that they are using? And you want to go home knowing this, obviously. So the F we're using, actually, as we're looking at the dual problem, we're defining F, the conjugate of F, not F. okay? So there's something quadratic, that's why what I mentioned earlier. And here is the F star that we choose. So here, what we're doing is, in the end, we hope to catch the vertices of this set. So one way to catch the vertices of a set is to maximize or minimize linear functions, okay? If you minimize or maximize a linear function, typically its maximum will be reached at the boundary. And if you're lucky, it will be reached at the vertices. Why? Because there are just a few cases that do not work. If the linear function is led by a vector that points toward the faces of this set, then maybe indeed the optimal points are all over the boundary. But if P doesn't point towards the faces, say P is like this, then certainly your maximizer will be here, okay? So this is also a key idea in linear programming. Okay, so now here comes the cost that we use. And again, we were as excited as you are now, because we were defining F star and we didn't know what the F was. So what we do to compute F, we take F star star, because we know this is what gives us F, and we compute and we get this. So we get that we are brutal in terms of enforcing the non-negativity constraints. And there is another term that's, once you look at it, you're like, yeah, of course I could have found it. But I mean, this is always easier once you actually see the formula. You can understand why this comes up. It's kind of natural, but it's still a bit complicated. So clearly it was not obvious to come up with this, directly. So what we get is this. That's somehow the cost that appears naturally. That's how we penalize controls. And indeed, if this cost is less than some capital M, then this means that, and for a positive U, then it means that 0 is between 0 and M, because its infinity norm has to be less than M, and its integral has to be less than M times ML. So clearly this is related to the initial problem we had, right? So we were like kind of relieved to see, okay, this makes sense. But yeah. Okay, and then, as I said, we are left with two things: show the coercivity of the dual functional, and then study the optimality conditions. So I don't have enough time to enter into the details. This is the technical part of the work, but then we can actually go on and prove this. In the end, you can actually, what's interesting is that you get controls that are shapes. So you prove that the controllability results, but also this is a constructive approach. What it means is that you can solve the dual problem. You get an optimal, what we call PF star, and then you can compute the control from that. So this is what we intend to do also numerically. So this is a constructive approach to see what the control, the optimal control is, this thing that will bring you, this shape control that will bring you to the target. Also, let me mention that we've slightly generalized this result, because you could say what's not satisfactory here is that the amplitude varies with time. So you might want to prescribe an amplitude at the beginning and then just move your action of the control over time. And that we can do as well. So we can have here one M star, which does not depend on time. Okay. And yeah, so the dual, which means actually for another cost. So we choose another F, but that's very close to the one that I mentioned. And then you get another dual problem, which will have its own maximal set. And then essentially, yeah, you'll get the same formula, but with an M star. And also everything can be computed from the dual equation. Okay, so I'll just mention that we are trying to generalize these results to other control problems, related control problems on the heat equation. And you saw that most of my presentation was abstract. Only at the end, I would tell you, oh, now we look at the heat equation, and actually you haven't seen exactly where the heat equation comes into play, like really comes into play. So obviously there is something a bit general here, and we're trying also to generalize the approach and have like general kind of general methodology and apply to different types of equations, types of constraints, and so on. So this is ongoing work. And also we want to better understand how this thing that we manage to deal with non-convex constraints, but is it Is it a very, systematic approach or not? It's still kind of a puzzle to us at this stage. And I guess I'll stop here. Thank you.